DB2 performance problems come in many different flavors. There are different causes and there are different solutions. And there's a lot of design techniques and programming techniques to get good performance in the first place. But of course, not all of you are developers or yourself always follow those techniques. And some good design techniques and tuning tips are very well known and talked about a lot. But I've run into a lot that are not described often. And some I had never seen before until I ran into them. And so that's what my presentation is about. Some of the things that are either my favorites, because they're a little bit different, or some are more common, but they're still my favorites because I think they're very important. And we don't have to go through the objectives. We'll see as we go along what we're doing. So it's a mixed bag of different things. First, I'm going to talk about arrays. Arrays are very common in programming languages, Java, C, whatever, but they only have limited support in relational databases. Certainly, you can have arrays within XML or within JSON, but you cannot have an array column in a table. It's not part of the relational model. But there are other ways that DB2 supports arrays. You can have an array data type. And in a SQL stored procedure, for example, and they can be passed in as a parameter to a SQL or a Java stored procedure or function. And how are they useful? Well, you might have a set of customer IDs or account IDs for which you want to retrieve information from one or more tables. So the front-end code may pass in this array of account IDs. And then you can combine it in your SQL statement. But one problem is you can't reference the array directly in a predicate. Have any of you worked with arrays in stored procedures? Okay. But there's a simple solution. There's a built-in function called unnest, which will take an array and it will return a temporary table. Similar to the XML table function for converting XML data into a table to join in a SQL statement with your relational tables. And so as an example, you can create a type, which I'm calling ID array. I'm going to hold big integers, and it's an array, and I'm giving it can hold up to 100. You can define it, I think the maximum is 2 gigabytes, 2 million rather, elements in the array. 2 million, 2 billion, I don't remember which, but it's large. Here's a procedure. I'm passing in a variable called cust_IDs of type ID array. We'll select the customer ID and a couple of columns from the customer table where the customer ID is in, and this is where I'm selecting cust_ID from unnest of the array cust_IDs. I give it a table reference. The table reference is list, and with one column called cust_ID. And arrays can have more than one column in them, so you can unnest into a table with more than one column. And then you can have other predicates in your select statement. This is a subquery with an in, but you could also do a join. I could join customer to list. And that works nicely. But there's a performance problem. Here's this table returned by unnest, but what's the cardinality? When DB2 does its cost estimating, the size of your tables, your statistics, are very important, especially when you're joining tables. It has to decide which table to access first, which one second. So there's no way to actually tell DB2 what the cardinality is directly. So therefore, DB2 is assuming, for cost estimation, that the array has the maximum size it is created with. So this one, in the previous example, DB2 will assume 100 rows are in the array. And up to 1,000. If you defined your array as holding 100,000, for cost estimating, DB2 will assume 1,000. And again, it's for cost estimating, determining the access path. But the cost of getting 100 customers from a table is 100 times as much as the cost of getting one customer. So if you've got joining several tables, you have indexes and predicates on other fields, DB2 could end up picking the wrong access path. For example, if I've got an order system, and typically a customer might have hundreds of orders over time, a large customer, over time. But on the other hand, on any given date, the order date or the ship date, there might be thousands of orders for that day. So if I'm passing in only one or two customer IDs, which is usually what happens when people are doing this type of function, they want to be able to handle more, but most of the time it's only one or two, clearly an index on cust ID is the best way to go. But even if there are thousands of orders shipped on a single date and there's an index on that order date, using that index might be better than trying to retrieve 100 customers, if each customer has several hundred rows. And DB2, there's a good chance it'll pick the ship date. And so that's the wrong access path if you're usually passing in one cust ID. There's no cardinality to use, so what can you do? And I have a trick using selectivity. Okay, who here is familiar with the selectivity clause on a select statement? Okay, so most of you are not. The filter factor in DB2 is DB2's estimate of what percent of the rows will match a given predicate. And based on that filter factor, it determines the cardinality of how many rows are going to be returned from that table. And that's the most important thing in DB2's determining which order to read the tables, which indexes to use. So I throw on, selectivity is a clause, a special clause that lets you tell DB2 what the filter factor should be for that predicate. And it's very useful in several cases where DB2 has trouble determining the filter factor. So I throw in a completely unnecessary predicate in this case. I say where cust ID is not null, because if it's in the array, if it's passed in, it won't be null. And I give it a selectivity of 0.01, which is a filter factor of 1 out of 100. If my array was bigger, if it could hold up to 1,000, I would have said 0.001. So that's telling DB2, assume that only 1 out of 100 will be returned. So therefore, it's going to assume that only one row will match that predicate. And that's how I'm telling DB2, expect only one row from that array, from the unnest. Now, there are other places where DB2 cannot get a good estimate for a predicate. Now, in general, if you're having problems with DB2's estimates of filter factors, the best things to do are run stats and collect distribution stats, sometimes column group stats. And that's always should be your first thing to do to fix your filter factors. But sometimes DB2 just cannot get a good estimate. If you have host variables or parameter markers in your query, if you have skewed data, distribution stats tell DB2 for this value it's 80% of the rows, for this value it's 10% of the rows. But if you have a host variable, DB2 cannot use those distribution stats. So it has to assume an average value, which is fine if you have a uniform distribution, but if it's very skewed and uneven, that doesn't work so well. And the worst situation is a range predicate. If I say where purchase amount is greater than host variable, DB2 doesn't know if I'm asking for greater than 0, which will be most of the rows, greater than 50,000, which is only a few rows, it doesn't matter how many statistics you have in the table. DB2 doesn't know what you're asking for. So in those cases, in a lot of cases, it doesn't matter because it's not an indexed column, so it doesn't matter so much. And there's a clear best access path regardless. But other times it does matter. And with selectivity, you can tell DB2 what the filter factor is. Now, if you'd like to know more about filter factors and selectivity and how to improve your estimates, I did a presentation last year all about filter factors, how to improve DB2's estimate, how to use selectivity, how to do other things to improve it. And as Phil, when he introduced me, said I'm a member of the IDUG content committee. We put up new articles every week on a variety of topics, including some of the sessions we've recorded at past conferences. And my session from last year was put up in December of last year. So it's available, well, first off, you can look at just the proceedings and read it, or you can watch the YouTube video of my presentation on filter factors. I highly recommend it. Great viewing. So here are some examples. I'm selecting from orders where cust ID equals parameter marker and the ship timestamp is greater than parameter marker. I have indexes on both columns, and these customers have hundreds of orders, thousands per day. The cardinality, well, the filter factor that DB2 determines is also for a range predicate is based on the cardinality of the table. DB2 is making an assumption that the more rows you have in the table, the smaller the filter factor will be for a range. It's a strange assumption. Sometimes it's good, often it's not. So, for example, a timestamp usually has a very high cardinality. I mean, because it's to the microsecond. And if the cardinality, for example, is 1 million, the filter factor is 3 out of 10,000. If there happen to be 1 million rows in the table, DB2 will assume that 300 rows will meet the predicate on ship timestamp greater than question mark. But I said there are thousands a day, and often for a timestamp, you're asking for a big range, not a tiny range. You want all orders shipped in a day, or all orders shipped in the last week, or even last month. So you want a big range, and DB2 is assuming a tiny range. So selectivity is the best solution for that. In fact, if I asked for the last week, and there's 3 years of data, the real cardinality is 6,400 rows, not 300. With selectivity, I could put on and tell DB2 the selectivity for this predicate will usually be 0.0064, or something close to that. Now, do you have to be exact? And the answer is no. I mean, what you're looking for, again, this is a tool to use when you have to. And you want to keep things simple. And you're basically just trying to tell DB2 it's not a small filtered number of rows, it's a large number of rows. It doesn't matter if I say 0.0064 or if I say 0.2. You know, it's giving DB2 the right general idea. There's going to be a lot of them, not a little of them. Go use the cust ID index, don't use the ship timestamp index. In fact, sometimes, well, before we get to that, I just want to say there are drawbacks to using selectivity. For one thing, it's a moving target. Over time, the actual filter factor can change. Your data distributions change. The table gets bigger, but maybe it's a filter factor on open orders, and maybe your daily volume has stayed the same. So a percent of the size of the table is going to grow in time, but the number of open orders today will stay the same. Or vice versa. The table may not grow because you purge regularly, but your business is growing, so you now have twice as many orders per day that you used to have. Another drawback is that it's so easy to add to the query. If you're not good, or your developers are not good at determining the right filter factor, it's easy to make a mistake. But of course, you should always be checking your explains. Make sure you end up with the access path you're expecting. As I said, you don't need to be exact, and sometimes it's even useful to lie to DB2. And what I mean by that is, if you have a complex query with a lot of predicates, there may be 3 or 4 of them whose estimate DB2 has trouble with. And I could try to figure them all out and get them all right. But of course, a simpler solution is better than a more complex one. So I try the filter factor on ship timestamp, and DB2 still picks that index. Well, again, what I'm trying to do is just tell DB2 there's a lot of them. So if I say, with experimenting, ship timestamp selectivity 0.9, that's clearly way more, but that's what I'm trying to tell DB2 is there are too many of them, don't use that index. However, if you do lie, make sure you put a comment in describing what you're doing. Because if you're going to lie, at least be honest about it. Now, selectivity gives DB2 more information, but DB2 still picks the access path. And sometimes you still have trouble getting what you want, which of course does not mean that what you want is best. But there is another way to influence DB2, and that's with an op guideline. Is there anyone here who has either used op guidelines or know what they are? An op guideline is a hint. You are telling DB2 exactly what access path it should use. Should it use this index, that index, do a table scan, nested loop join, hash join? You are telling DB2 what to use. And again, there are times when it's absolutely necessary. Now, up until version 11, the only thing published in the IBM documentation was it's created to create this in an op profile external to the program, tied together at bind time. But you could also put it directly in your code right after your individual statement. And that's actually been available since version 9, but undocumented. But finally, with version 11, they decided to document it, and they're talking about it officially, because it's so much easier. Because if it's internal to your program, you know it's there. If it's external, connected at bind time, it's easy to forget about it over time. If the person who creates it is not the person who develops and deploys a new version of the code, if you change your code, it's not going to match, the statement text with your separate op profile. So you have to change it. So being inline is much better. And the way you do it is you put it in as a comment as the last thing in your statement, at the very end, right before the semicolon. It's formatted as XML. The node is op guidelines, and in this case, I'm joining tables T1 and T2, and I want DB2 to just do a hash join. So the hash join, I tell it which is the left table, which is the right-hand table, whether to use an index or not, or leave that up to DB2. Or in this case, I'm telling DB2, just do the table scan for both of them. Now, it's in the form of a comment right before the semicolon. If you put it in the wrong place, DB2 won't use it. If I put it after the semicolon, it won't work. It's not part of the statement. DB2's parser will just ignore it. Often the last thing you sometimes, if you are writing a query and you want to use the UR isolation level, that usually goes at the end of your query with UR. And I've seen developers put in the with UR after the guideline. that won't work either. If it's not the very last thing, DB2 will treat it as a comment and ignore it. Now, when you do an explain, a visual explain, DB2 returns diagnostics. If you have errors in your statement. And if you have a misformed op guideline, if I misspelled TB scan, or if I said table equals T3, and there's no T3 in the query, you'll get a diagnostic that says, your op guideline's not well formed, or the table's not found. If I put in this query with UR at the end, what diagnostic do you think you'll get? Any guesses? The answer is you won't get any error message. Why? Because it's a comment. You don't get error messages for comments. But if you check your explains, you're telling DB2, use this guideline, you want to check your explain output to see if it did use it. And did it use it correctly or the way you wanted it to use it? At which point, if you see it ignored it, then look to see if it's misplaced. Okay. Next topic, speaking of hash joins are very good for batch processing, where you're typically reading the whole table or a large portion of it. Nested loop joins are good if both tables are clustered on the join columns, so they're in the same order. But otherwise, you're going to end up with a lot of synchronous I/O, with DB2 jumping all around on the inner table, because it's in a different order than the outer table. So a hash join with table scans is often much better, because those tables will be read with sequential prefetch, in which DB2 is reading 32 pages typically per I/O, and it's asynchronous. DB2 goes and issues that I/O before it needs those pages and rows. So, as an example, reading 400 million rows with prefetch can be much, much faster than reading 1 million rows randomly. The way a hash join works is DB2 takes the inner table, which is the one on the right-hand side of the explain, and it reads through it, and for each key, it uses a hash function to find a bucket to place it in. So it builds a hash table with buckets. A key is randomized to that, and an entry is put in there. Now, more than one key could hash to the same bucket, in which case DB2 will chain them together within that bucket. If you have 3, 5 keys hashed to the same bucket, that's no big deal. But if your hash table is way too small, you could end up with thousands of entries chained together within a bucket. In which case, when after the hash table is built, DB2 reads the outer table, hashes those keys, looks in the hash table bucket, and then looks at the key values to find the one that actually matches that particular key. And if it has to search through thousands on a chain, your CPU time is going to go way up. So it's important that it be the right size. Now, how big is it? The number of buckets is equal to the DB2's estimated cardinality of what it's reading from the inner table. So it's not the cardinality of the table itself, but after applying predicates. There'll be filtering if you have predicates on that table. So the filter factor, your statistics and your filter factors have to be very accurate. So if you're off, as I said, by a factor of 100 or 1,000, you could end up with very high CPU utilization. So that's another case where you have to really look at your estimates from your explain, and if necessary, do something to improve those estimates. Another important thing is that the hash table comes out of sort heap. So you have to make sure your sort heap is big enough. So generally, it's better if the smaller table, after filtering, is in the inner table so that the hash table will be smaller. You'll use less sort heap. Okay, now we're going to look at a few things, some general things, a general guideline. Beware of grand pronouncements and generic solutions. A lot of experts and a lot of IBM experts tend to do that. They'll say things like, one big buffer pool is better than many smaller ones, so you should go with one big buffer pool. The first part of that is there's some truth to it. One big one is better than a lot of little ones. But the second part is not generally true, because it's well established that there are good cases for separating certain kinds of data. Particularly, you want to keep your catalogs in a separate buffer pool than your user tables, because you want DB2 to have quick access to its catalog, and for very different access patterns. Separating your tables and your indexes into separate buffer pools, maybe one for tables, one for indexes, is a good general practice. Same with temporary tables. And very large tables that are mostly processed sequentially, it's good to separate those out if you can identify them from your regular OLTP access tables. Now, with a very large table that's mostly processed sequentially, what I've sometimes done is put in its own buffer pool that can be fairly small in size, because that table may be so large that it's not all going to fit into your buffer pool no matter how big you make it. In which case, you're not going to get any reuse from the buffer pool. One table scan will fill it and start over again. Your next query, the beginning of the table is already out of the buffer pool, and so it's going to have to keep reading it and reading it. So you might as well make it small and not waste memory in that case. Now, you're not going to have a lot of tables like that, but you may have some. You may also have very large tables that have a lot of table scans, but they also do random access, a lot of it. So one solution for that is to use a block-based area of the buffer pool. Has anyone used that? A few people. And in fact, if you look at my speaking notes, you'll see that several top DB2 consultants, including Phil Nelson and Martin Hubel, have had very good success with even a block-based area as small as 1,000 pages. And what that is when DB2 is prefetching data, it'll put it into the block-based area. If you do random access, it'll go into the regular part of the buffer pool. So now this table can be in shared buffer pool with other tables, but the sequential processing is not going to mess up your usage of the buffer pool for everything else. Now, that's another one of IBM's grand pronouncements in the past was, there's no real use to the block-based area, just use the regular buffer pool. They didn't seem to get it. However, recently, Steve Reese, who's one of IBM's top performance people, did concede that there could be some uses for it. And a few months ago, he wrote a blog post for us. It's on the I.Content blog, and that's the URL, all about performance and using the MON report modules. But he does mention that there can be useful cases for the block-based area. So where did this idea of one big buffer pool come from for everything? Well, other than the things I talked about, it's often, if you separate things further, maybe this schema in this buffer pool and this schema in another one, where let's break it up even finer. In order to do that well and get good results, you have to do a lot of analysis and a lot of testing. The drawback of a lot of separate buffer pools is you're not going to make as effective use of memory, because different tables, different applications are going to have different times of day when they're in heavy use and when they're in light use. And if a table is heavily used in the day and hardly used at night, that memory is going to waste if it's dedicated to that table. Another application may do a lot of processing at night as well as in the day. So, you're just not making the best use of memory if you have the time and the expertise to analyze it further, you might be able to separate things further and make good use of it. But otherwise, start off with one for tables, one for indexes, and go from there. Partition indexes. Range partition tables are very good for a number of cases. For a large table, you can have smaller amounts of data in each partition. You can do some utilities on certain parts. Maybe search less data if you have predicates on the partitioning columns. And purging and archiving could be easy. If you want to regularly purge data whose order date is older than a certain time, if you partition by order date, you can just roll off that partition. Indexes on a partition table can also be partitioned or global, non-partitioned. And another IBM grand pronouncement is all your indexes on partition tables should be partitioned. And the reason why is because partition rollout, also called detach, is going to be much, much faster if all the indexes are partitioned. Okay, that's good. And your index trees are going to maybe have fewer levels, because each partition of that partitioned index is a separate index tree. Fewer levels is good for performance. But your online queries may be a lot more costly. If all of your queries have a predicate on the partitioning column, you'll get partition elimination, and DB2 will only have to look at those partitions that meet that predicate. But if your query does not have a predicate on it, then all of the partitions have to be searched. If I have 20 partitions, DB2 has to do 20 index tree searches instead of only one. And for an online transaction, that's not good. So that means several things. First off, choose your partitioning columns carefully so you can take advantage of partition elimination. If you can't come up with a good one that will work, then for at least some of your indexes, a global index is much better. Going back to that as an example, and this is about choosing carefully. An order system, we've got a created date, an order date, a last modified date, and a ship date. Which one do you want to purge by? Well, that's a business requirement, but sometimes some places will pick created date. You know, it's easy. Or last modified date. If they last touched it, that's when we'll purge by. It's unlikely you have predicates on last modified date. You may have predicates on order date or ship date. Customer calls up, where's my order? And they'll say, when did you order it? And they'll say, September 2nd. And this application will build in a predicate and look for the orders whose order date is greater than September 1st. But in the meantime, if you've partitioned on last modified date, no partition elimination. Now, sometimes the application can throw in a predicate. Not in the last modified date. That one's too tricky. But if it was, let's say they did order date or created date. Well, let's say they did created date. And there's a predicate in the code already for order date greater than September 1st. You could safely, in the application, throw in a predicate where the created date is greater than September 1st. Because you certainly didn't order it before the row was created. But sometimes you don't have such a predicate. And sometimes it's not easy. So try. But that's very important that if you've got that sort of situation, try to make your partitioning match the predicates you're going to use. Now, some other index design things. there's always been a long debate, should you use business keys, like your order number and your customer number and so on, or should you use surrogate keys, generate a sequence number for the customer and for the order and for the item. When object-oriented was big, people were saying, every object intrinsically has its own ID, so let's make a global, ID for it. The problem is that the biggest factor in performance is I/O. And if you're joining two or more tables, if they're both clustered by the join column, you're going to get, for example, customers and orders. All of the orders for the customer are going to be mostly stored near each other. And so if you're trying to read all the orders for a customer, you've got 1 or 2 pages you're going to have to read. If the order number is stored by order ID, they may be spread on, 100 orders might be on 100 different pages. And then the item table, if you have a generated item ID, those are all going to be on separate pages. So for performance, the best design would be to have the cust ID, even if it's a generated column, but have it present in all 3 tables, and the clustering index should start with cust ID. And that way, his orders will be near each other. Non-unique indexes are stored with 1 entry per key value in the index, followed by a list of row IDs for each row with that key value. And those RIDs are maintained in row ID order, in physical order of the row. If you have a low cardinality non-unique index, there are many drawbacks, especially if the key is frequently updated, like status. All the orders start off as open. Eventually they're shipped or fulfilled. So you're always updating it. So it's low cardinality. That chain of RIDs is very long. To update it, Db2 has to search the chain to find the one for the row being updated, has to delete that one, and insert a new entry in the right place in its chain. To make that perform better, it's a good idea to have additional columns in the index. It'll make separate index entries for them. Db2 can then find it more easily, especially if it's a key column. If you want to update the status for account number 27, and the index has status and account number, Db2 can use both columns to find the right spot in the index. Plus, you can also get better filtering from the index often, and maybe even get index-only access. If your predicates also have not only status, but order date, have order date as another column in that index. And so if you're only looking for open orders from today, or that are older than 3 days ago, Db2 will do that filtering while processing the index instead of having to look at all open orders for the customer. There's also a good chance you're going to reduce lock weights. Because if you have a lot of concurrent updates, inserts and updates to that table, all with the same status, and Db2 has to position it in the right spot within that chain, there's going to be locking and lock contention on that index. So why do people have low cardinality indexes? Well, sometimes it's to find the open orders. And again, if you have more columns in that index, ID columns, you can still use that index. Another important thing is make sure you've got distribution stats and that you use a literal and not a host variable for that column, for that predicate. Because if you say, find me the ones where status equals parameter marker, and you always pass in open as the value, but Db2 sees parameter marker, it has to assume a uniform distribution. And it's not going to use that index anyway. Because even though you only have 100 orders open, the average, is probably 50,000. And another reason is sometimes some places create indexes on all kinds of columns that have predicates, and that's overkill. Too many indexes. Because if DB2 doesn't use that access path for any of those queries, because it's not the important filtering, then that index is of no use. In 10.5 of DB2, they introduced index on expression, where you can create an index based on an expression, such as upper of last name. And then if your query has a predicate that matches the expression in the index, DB2 can use that index. In the past, what you'd have to do is create a new column, maybe generated automatically, in which you take the last name and translate it to uppercase and store that. But not only do you have to do that, but if you have existing code, your programmers have to go and change that code to use that new column. And with this, you don't have to go through that. It's a great feature. How many here were in John Hornibrook's presentation yesterday in which he discussed it? He discussed it as one of his favorite tips, and it's because it's good. When DB2 10.5 came out, I wrote a blog post for the content blog on my favorite top 10 performance tips for DB2 10.5. And at number 2, I put DB2 Blue. And that's all anybody was talking about. At number 1, I put index on expression. Because it's something, a lot of you don't have Blue. You don't have columnar tables. But everybody has indexes. And this is something you can all take advantage of. In general, if you have an expression involving your column and your predicate, column plus 3 is greater than host variable, etc., and so on. In general and in the past, that meant DB2 could not use that index. But in recent versions and in these examples, some of these have been available since 9.7, DB2 will now automatically, during query rewrite, will take some of these predicates and convert them into things you used to have to do manually to make them indexable. If you want to get the year from a date column, it becomes date columns between January 1st of that year and December 31st. Similarly with a timestamp. And if you have literal between 2 columns, in the past that couldn't be indexable because you have 2 different columns, but now that'll be rewritten as the literal, such as current date, is greater than or equal to column 1, and greater than or equal, and column 2 is greater than or equal to current date. And then if there's an index on either column 1 or column 2, DB2 could use it. Substring at the beginning of a column also becomes a greater than and a less than. So these DB2 will take care of for you, but in other cases, if you have expressions that DB2 is not translating, you might want to do similar techniques so that your column is by itself and the expression is all on the other side of the operator. Speaking of dates, there's difficulty with recent dates and timestamps and the filter factors. This is not just true of DB2, it's true of any DBMS. The less up-to-date your run stats are, the less accurate the filter factor will be. If you run your run stats regularly every weekend, and today's Thursday, and I want to find all things that happened 3 days ago or more. No, or I want to find all things that happened in the most recent 3 days. Find me the things that were entered in the last 3 days. So I'll have something like where the column date is greater than or equal to current date minus 3 days. If today is Thursday, according to the statistics in the catalog, there are no rows because I ran them on Saturday or Sunday. So that's a place to be careful with your filter factors if you're getting a bad access path. Obviously, you don't have to check all your filter factors for every query, but where you don't end up with the access path you'd like, that's where you care about it. Current date is also tricky because it's treated differently for static and dynamic SQL. For dynamic SQL, the actual date or timestamp, for current timestamp, is what's used for the filter factor calculation. But for static SQL, it's treated as a host variable. Neither one's completely accurate. Again, if your run stats was a week ago or a month ago, then using the current date, your filter factor is going to be too low. If it's a host variable, DB2 assumes an average value, so there's a good chance your filter factor will be too high. So again, these are tricky and things to watch out for. User-defined functions come in two flavors, deterministic and non-deterministic. A deterministic function is one in which, for a given input value, the function always returns the same output value. A non-deterministic is one is, for the same input value, you may get a different value at different times. And here's an example. A deterministic function, I'm passing in a status. The function says, if it's open or pending, return a 1, else return 0. So assuming there are 10 different statuses, for any given status that's passed in, the result will always be the same. So that's deterministic. A non-deterministic function would be age. You pass in the birth date. If I invoke that function today, I'm going to get a different output than if I invoked it last year or next year. If DB2 knows the function is deterministic, it'll cache your inputs and your results. And it doesn't have to invoke the function at all. And especially if that function is complex or costly, you can save a lot of CPU time. And even for a trivial one, you can still save a good amount of CPU time because you avoid the invocation and execution. But the default is non-deterministic. So if you have a deterministic function, make sure you declare it as deterministic by using the keyword deterministic on the create function. However, that keyword's only available on a standalone UDF. If you've created a module that has stored procedures and functions and so on, related ones, there's no place to put deterministic on those functions. So for those, it might be better to break it out and make it standalone, where you can tell DB2 that it's deterministic. Moving on to reorgs. Do you all do in-place reorgs? Is there anyone who doesn't? Okay. And offline reorgs are a lot faster than in-place, but in-place have much better concurrency. Your online transactions can work, but they can be slow, especially if you're on slower I/O system. And that's because the reorg is doing four things. If you have a clustering index, it'll reestablish clustering. The second thing is it eliminates overflows. Overflows happen if you update a row and its new size is bigger than the old size and there's not enough space in the page, DB2 will leave an anchor on that page, move the row to another one. And it does that so that real time it doesn't have to update all the indexes to point to the new page. But that means when you go to retrieve that row, DB2 has to go to 2 pages to get it. And that's especially a problem for table scans. If you have an online transaction that's reading 1 or 2 rows and it has to do 2 pages instead of 1, it's not that big a deal. But a table scan is with prefetch, asynchronous. If it comes to one that's an overflow, it has to stop and do a synchronous I/O. So cleaning up your overflows is very important. But DB2 does 2 more things on the reorg. It also reestablishes free space if your % free is greater than 0. And it does that by, if the page doesn't have enough free space, it has to move rows elsewhere. And if you have too much free space because you've deleted a lot of rows, it moves other rows in to fill it up. The things you mostly care about are clustering and overflows. And if you mostly care about overflows, there's an option that started with 10.5 called Clean Up Overflows. And that's the only thing DB2 will do on that particular reorg. And it'll be much, much faster. On an earlier release, I tried to simulate that by using %free0. I didn't leave room for growth, which meant, I got a slightly higher rate of overflows, but now my in-place reorg was much faster because it didn't have to reestablish free space. So I had much less to move around. But again, starting with 10.5, you can do clean up overflows. Now, on run stats, if you don't care about completely accurate statistics, you can speed up your run stats with the table sample option. It tells DB2 to only sample either a percentage of the rows or a percentage of the table, of the pages. And it makes the run stats much faster. The lower the percentage, the faster, but the less accurate the statistics. But if you're having trouble fitting in your run stats, that's something you could look into. Did you know that you can put it on a select statement too? If you have a query where you don't need the exact answer, you just want to count how many rows approximately do I have in this 2 billion row table. You don't care whether it's 2,000,000,007 or 2,000,000,023. So put table sample on your select count. If you want to pull out a subset of data for testing purposes, but you don't want it all to be, you don't want to just say fetch first 100,000 rows because your data is different later in the table over time. You could do table sample instead and get a selection from different parts of the table. Hey, I'm running a bit behind. The package cache. How many people here use the package cache for your performance analysis? It's the best built-in tool for analyzing your performance. It's a table function that comes with DB2. There's one row per statement. It's cumulative. It's used for two purposes. The primary use is for dynamic statement reuse. If DB2 finds the exact statement in the cache, it doesn't have to re-prepare that statement. The secondary use is for metrics. It's cumulative. That one line for that statement will have totals since DB2 was recycled. How many executions there were, how much total CPU time, elapsed time, and so on. If the cache is full, if you didn't size it big enough, statements are going to get flushed frequently to make more room. Even if you did make it big, it will fill up and older ones will be flushed. But also, if a statement can't be reused because you've done run stats or you've done a rebind, then it gets flushed. And so if you're using it for performance analysis, they told me to use it for performance analysis. Why are they flushing my statements? But if you need every single one, that you can create an event monitor, a package cache event monitor, which will capture every statement as it's flushed from it. But, that's overhead. Pain in the neck. So there's a limitation. And there are some good performance monitors out there, but there are also some that aren't quite so good. Now, there are, as I said, metrics for wait times, elapsed times, how many lock waits there are, how many IOs, broken down between data and index and temporary, physical and logical reads. The physical read is the actual IO. The logical read says, I need this page, and at first DB2 looks in the buffer pool. And if it finds it there, that's it. It doesn't have to do the physical read. Some of the performance monitors, like Data Server Manager, which still need some work, They give you the columns that they think you need. I want all columns available, and that's why I like the package cache. Because there's all different kinds of problems and all different causes. And I don't necessarily know ahead of time which ones I want. With the package cache, since it's a table function, you can run SQL against it with where clauses to pick out the top consumers by total CPU time, or you can calculate the average in your predicate, total elapsed time, activity time, or total CPU time divided by num execs. Or you can select the entire package cache and export it as a CSV file and open it in Excel, where you can sort them and do finds based on statement text or package name. So which ones should you select? Well, select asterisk is easy, but there are a lot of columns. In DB2 9.7, there were 64 columns. Now there are 277. If you do select asterisk, that's very wide output. Whether you're looking at it in Data Studio or Excel, you're going to be doing a lot of scrolling back and forth. So it's maybe better to list the columns that you think you want or that you might want. But you don't need them all. If you're not running pure scale, you don't need all the new columns for pure scale. If you're not running blue, you don't need all the columnar table-based columns. Now, which ones are most useful? Well, there are two primary cases. One is if you have a poorly performing statement that you know about, someone told you this thing's running slowly. You want to do a deep dive, look at everything, all your clues. The other use case is for you to identify things that are poorly performing, that are meeting the SLA, so no one's complained, but it's taking too much time, too much CPU time, too much lock weight. And different columns are useful for one or the other. Performance is based on time spent. So we have metrics on time spent. Other metrics are good for analysis, but don't represent actual time. And therefore, for identifying candidates, they'll actually give you probably more false positives than real ones. So to identify ones, I look at time spent metrics. When I'm analyzing a given statement, I'll look for all the other columns. So for example, rows read divided by rows returned. Some people call it read efficiency. You know, if DB2 has to read a lot of rows to return only a few, that's not efficient. But a high ratio doesn't always mean a problem. If you have a batch job reading the whole table with predicates and non-index columns, you have to read every row. It's going to be high. If you do a select count, rows returned is 1. So if you just pick out the ones with high read efficiency, you know, you're going to waste a lot of time looking at things that are not problems. Same with rows read. Who cares? I don't care how many rows DB2 reads as long as it does it efficiently. Or maybe it needs them. For a given individual statement, it could represent the problem. So I will look at those when I'm analyzing a particular statement. Logical reads is similar to rows read. If it's in the buffer pool and query is fast enough, who cares? But if it's really unusually high, there's probably a problem. If you have 3 large tables totaling 500 million rows, but the package cache shows 2 trillion rows read, maybe you have a nested loop join with inefficient access to the inner table. And so you're reading way more rows for each one. Hit ratio for the buffer pool. Now, hit ratio is not a column, but it's easy to calculate. A ratio is not a measure of time spent. It's the physical read that takes time. If you have one access path with 10,000 logical reads and 2,000 physical reads, That's an 80% hit ratio, which isn't too good. But my other access paths will have 1 million logical reads and 50,000 physical reads. That's a 95% hit ratio. That's much better. But it's going to take 25 times as much elapsed time, because it's 25 times as much physical reads. So hit ratio is a good indicator of buffer pool performance in general. Maybe it's too small and so on, but not to identify problem statements. And it could mean, a high number of physical reads could mean the buffer pool's too small, bad table or index design, bad program design. I mean, a lot of different reasons, reading more data than necessary. The elapsed time comes with two important columns, statement exec time and total activity time. The difference is that total activity time is the time spent for this individual statement. Statement exec time is time spent for this statement plus everything it invokes. So if this statement is a call of a sort procedure, the total activity time is really small. The call doesn't take any time, but the statement exec time could be this big because the things inside it are taking time. And I've already talked about some different options for them. To get more out of the package cache, it's cumulative, so averages are important. So divide by num exec. But if you want point in time, or a small period of time, you need to get deltas between two consecutive time periods. So you could collect it twice. You could collect it daily, or every hour, or every minute. And then you could look at two consecutive rows and calculate the delta. You could do it manually by putting it in Excel and subtracting. That's a lot of work. Or you could load it into a table along with a timestamp of when you captured it, and then do a query on that table joining two rows where one is the next row after the other. And if you're going to do that, calculate the delta when you insert it into that table. So now you can get the deltas more easily with a simple select. And you can get the deltas of the total or the average of the deltas. And you can even do trends and spikes. I did one where I joined two consecutive rows where the second one is X% more elapsed time than the first one. And that'll show me where suddenly this minute it spiked. And that's it for now.
Thank you. Thank you.
Thank you.